Hello and welcome to the Open Heat and Mass Transfer course, now with the topic of diffusion. This is a course brought to you by Albert Aachen University and the University of Twente. My name is Wilco Roves, and in this video we will show you the derivation of the conservation equations for mass transfer and the analogy to heat transfer and also to momentum transfer. What are the learning goals in this video? First of all, we will show you and give you a fundamental understanding in the necessary steps to develop the conservation equation. If you have severe problems with that, we kindly refer you to the heat transfer lectures in which we do this in a much more detailed way. The second part is that we look at the common features between heat, mass and momentum transfer. Let's start with a practical example. Here we see an image of an oven, a diffusion oven, which is used to produce semiconductors and solar cells. There is an explanation of what's happening here in this schematic. The key part of it is that we have a kind of material that should be sedimented or that should diffuse onto the silicium wafers, and that we heat these two compartments in order to drive this material towards the location with this flow assistant driving, and then it will, due to the higher temperature, diffuse into the material, which is the aim to bring the material towards those silicium wafers. So in the next step, let's see how we can develop the differential equation for diffusive mass transport in a one-dimensional domain. So how does this procedure look like? First of all, and that's the initial step always, is we define a control volume. Then we will define the relative flows and fluxes that enter or exit the control volume, or we check whether there's a source inside or maybe an unsteady part with the change of a quantity inside the control volume. Next step is that we use this to set up the balance, now not the energy balance but a mass balance, and finally from the balance and the fluxes we will develop the differential equation. So after showing that, let's do that. Of course, finally we solve the differential equation with the required boundary conditions. Let's look at the control volume. We do it very simple. We have this cube here, we have a specific height dy, we have a length dx, and we have a width dz. And in this control volume we have an inflow of mass. Here the J stands for the mass transport by diffusion. So we have an inflow, area specific, that are the two dashes, and we have an outflow. The inflow is taking place at the location x, the outflow is taking place at the location x plus dx. So very similar to what we have learned for the heat flows. Now if we look at the steady state case, there are only two flows involved, the inflow and the outflow. So we write on the left side 0 is equal then to, on the right side, inflows minus outflows. Now in the next step we have to define those two fluxes. Let's say the inflow here, for this we use Fick's law, as we have realized this in the last lecture, is equal to the negative of the diffusion coefficient times the gradient, the local gradient of the partial density rho I, or we can change this partial density to an average density and the mass fraction xi. To obtain the other flux, the flux at the location x plus dx, we will utilize the Taylor series expansion as known from heat transfer. So both together, if we add them, we are left at the end with the knowledge that the change of the mass flux dj double dash dx is equal to 0, and so we can put this change, including Fick's law, we can have from the first gradient of the mass flux, we end up with a second gradient of the density, or with a second gradient of the mass fraction Xi. So the equation that is finally resulting is that the second gradient of the mass fraction with respect to the spatial coordinate is equal to 0, and then we have the density and the diffusion coefficient that are the scaling parameters, but as you see, they can be dropped if we just have a 0 on the side. But for the sake of completeness, we show that, because in the next step, if we now look here at transient mass transfer, we will have an additional term. We have the change of the mass inside the control volume by time. How can we express this change? So the mass is nothing else than the partial density times the volume inside here on our control volume, and the control volume is defined by dx, dy, dz. Now, from the balance, again, now we have not 0 on the left side, but the change of the mass with respect to time is equal to the balance of the flows. Utilizing again Taylor's series expansion, we end up with the following equation. We have here on the left side the change of the density versus time, and we see that these dx, dy, dz, they cross out due to the fact that they are also here the areas remaining in the flux, and the dx comes from Taylor series expansion, and thus we have on the right side the negative of the change of the fluxes with respect to the spatial coordinate. Now we can express the change of the fluxes again as using Fick's law with the gradient in concentration, and thus we end up with an equation that the change of the mass fraction dxi dt, which results from dividing the partial density by the density itself, is equal to the diffusion coefficient dij times second gradient of the mass fraction divided by the spatial coordinate times square. Now that is the derivation. Now we see that this equation looks very similar to what we have seen already in heat transfer. We have the temperature change over time is equal to some kind of thermal diffusion coefficient times the second derivative of temperature. And so that we can now compare all those equations. We have, as mentioned here, the second derivative with respect to x times the thermal diffusivity is equal to the change of the temperature in time, and we know that the unit of the thermal diffusivity is equal to square meter times second. And for that, if we look at the profile that will result from Fourier's law, we have here a heat flow from the wall towards the fluid, and we have fluid on top. We will have a much closer look into that in the lecture of convection. Then we have the boundary layer, the thermal boundary layer with the thermal boundary thickness delta T, and we have the temperature in the infinite location. And so we have a temperature profile from the wall temperature towards T infinity. And of course, this is then described here by Fourier's law. In transient mass transfer, it looks very similar because we have a change in the mass concentration divided by the time is equal to the mass diffusion coefficient times the second derivative of the mass concentration with respect to the spatial coordinate x. Here, the d, the diffusion coefficient, is also in the same unit as the thermal diffusivity. And if we look here on the picture of the convective flow, we see that the picture is nearly the same, only the temperature is changed to the mass fraction xi, and this here is at infinity. Here we have at the wall a specific given concentration, and there's no difference, so we can use a lot of knowledge that we had learned for heat transfer also in the mass transfer description of problems. Now I would like to also show you the part that is coming from fluid dynamics, the momentum transfer and the momentum transfer in the boundary layer in the unsteady cases, that du dt is equal to the kinematic viscosity, or also known as momentum diffusivity, times the second derivative of the velocity with respect to the spatial coordinate. And again, here you see that the momentum diffusivity has the same unit in meters squared per second. And also the image looks very similar. We have the development of the boundary layer, and we have here our profiles, but of course we display this because our assumption is that we have a zero velocity at the wall, that the velocity increases from the wall towards the environment or the infinity location. We could have the similar panel here if we just assume that the wall temperature is lower and we have a cooling, and from that we would have similar profiles also for temperature or for concentration. And with that, I'm finished with the video. I would like to end with a few questions, or here with one question. And the question is, what is the analogy of diffusion coefficient in heat transfer and momentum transport? So we have learned this in the last slide, that the diffusion coefficient combines in a differential equation the change in the concentration or temperature in time with the spatial change due to diffusion. And in this case, the coefficient has the same unit, meter square per second. And with that, thank you for your attention. Have a nice day.